A mud brick dome stands in an Iranian desert under a summer sun hot enough to push the air toward 45 degrees Celsius. Yet below that earthen cone, a Yakhchal could hold stores of solid ice made without electricity. The trick was not to create cold air inside the dome. It was to control where heat went. On a clear desert night, exposed water can radiate infrared energy toward the sky. The effective radiative temperature of that sky may be far colder than the air beside the water, so the surface can lose more heat than it receives from its surroundings. Dry air can also make evaporation useful, while shade and earth limit the heat returning from the daytime environment. Under favorable conditions, those losses can bring water down to freezing and help it cross that threshold. But freezing is only the first difficulty. How could a limited window of nighttime heat loss remove enough energy from a volume of water to produce ice? And once that ice existed, how could it survive months of sunlight and scorching air inside a structure made largely from earth? The answer begins with a simple shift in perspective. The Yakhchal was not a refrigerator hidden inside a dome. It was a timed heat management system. Expose selected water to the night sky, shield the result from the sun, and slow every path by which warmth could return. The difficult part was not merely lowering water from a hot afternoon temperature to 0 degrees Celsius. Freezing demanded a second, much larger payment from the energy ledger. Take 1 kilogram of water beginning at about 20 degrees Celsius. Cooling it to the freezing point removes roughly 84 kilojoules of sensible heat. But once the water reaches zero, it still is not ice. The phase change requires about 334 kilojoules more, the latent heat of fusion. In this simple example, nearly 4 times as much energy is removed during freezing as during the initial temperature drop. That distinction changes how the system should be imagined. A surface of water can become cooler than the surrounding air because its energy is being distributed among several paths. It can radiate infrared energy upward, exchange heat with moving air, lose energy through evaporation, and conduct heat into or out of the ground. Air temperature describes only one part of that exchange. The surface has its own thermal balance. During the day, sunlight and hot air usually push that balance in the wrong direction. At night, especially under a clear and dry sky, the outgoing terms can dominate. But the useful question is not whether one mechanism sounds powerful enough to make ice. It is whether the combined nighttime losses can first remove the water's sensible heat and then continue removing energy as liquid turns solid. The Yakhchal therefore did not create a loophole in thermodynamics. It arranged the timing. A limited area of water could be exposed when the sky offered the strongest opportunity for heat loss, while the surrounding structure reduced unwanted gains before and after that window. The process was demanding but not impossible. The system had to collect many modest advantages and direct them toward one unusually cold surface. A cutaway view makes that division of labor visible. Above ground stood the recognizable conical dome, often built from thick earthen masonry and finished with a durable plaster or mortar layer. Around it could be additional walls, shaded approaches, channels, and openings. Below it lay a deep chamber where ice and sometimes chilled goods could be protected from the desert environment. These features were not simply different parts of one container. They served different thermal jobs. The upper zone was the active interface with the outside world. It could shelter water from direct sunlight while allowing selected surfaces to exchange heat with the night sky. In some examples, water was associated with separate shallow areas rather than being placed directly into the deepest storage space. That arrangement makes physical sense. A broad, exposed surface is useful for losing heat, while a deep pit is useful for keeping an already cold mass away from heat. The lower chamber performed the opposite task. Its depth surrounded the stored ice with earth, reducing direct contact with hot air and delaying the arrival of heat from the surface. Access routes could be narrow or controlled, and the heavy envelope added thermal inertia. The ice did not need the entire building to be cold in the way a modern refrigerator is cold. It needed heat to arrive slowly enough that the remaining mass could survive the season. The dome helped manage the boundary between those two environments. Its height increased the amount of material between the exterior and the protected interior, while its form limited some direct solar exposure compared with a broad, flat roof. Walls and orientation could create additional shade, though their exact arrangement varied between sites. The key is not one universal blueprint. It is the separation of functions. Expose or ventilate where cooling was wanted, add mass and shade where warmth was dangerous, and place the long-term reserve below ground. Seen this way, the Yakhchal resembles a thermal system with a cold-making zone above and a heat-buffered reservoir below. The visible dome was only the part most people could see. Much of the preservation work happened in the earth beneath it. The night sky supplied the most unusual part of that system because it was not simply another mass of air. It was an infrared view toward the atmosphere and through a relatively transparent atmospheric window toward much colder space. Every surface emits thermal radiation. The amount depends strongly on its absolute temperature and on how effectively its material emits at infrared wavelengths. The atmosphere sends radiation back downward as well, but water vapor and clouds make that return stronger. They behave, in effect, like an infrared blanket, not a solid cover, but a layer that absorbs and re-emits more of the energy rising from the ground. A dry, cloudless sky is different. With less water vapor and no cloud deck, the downward infrared contribution can be smaller, so an exposed surface may lose more radiation upward than it receives from above. Its radiative temperature can therefore be lower than the ordinary air temperature measured beside it. That does not mean the surrounding air has frozen or that the sky itself has a single physical temperature. It means the surface is exchanging radiation with an effective radiative environment colder than the nearby atmosphere. This is why a surface can sometimes cool below the air temperature on a clear night. Air still moves across it and tends to bring heat back through convection. The ground may conduct heat toward it. Evaporation may remove additional energy. Whether the surface actually reaches freezing depends on the balance among all of those flows. The conditions matter. Clear skies expose more of the radiative path. Low humidity reduces atmospheric interference. Calm or managed air can limit the rate at which warmer air replaces the cooled air at the surface, while an unobstructed view of the sky gives radiation a larger escape route. Under cloudy, humid conditions, the same water and masonry would face a much less favorable balance, so the desert night was not inherently cold enough by ordinary weather standards. It was useful because for a few hours it could make the upper surface radiate toward an environment colder than the air surrounding it. The Yakhchal's geometry and operating habits had to preserve that advantage rather than smother it. The Stefan-Boltzmann relationship makes the radiative part more concrete. Emitted power is proportional to emissivity times the Stefan-Boltzmann constant times absolute temperature raised to the fourth power, epsilon sigma T to the fourth. The fourth power matters because small temperature changes can alter radiative output, though it does not by itself prove that a surface is cooling. A surface near room temperature can emit several hundred watts per square meter of infrared radiation, and water is a strong emitter across much of this range. But the surface also receives radiation from the sky. The useful balance is outgoing surface emission minus downwelling sky radiation. alongside convection, conduction, absorbed sunlight, and evaporation. On a clear, dry night, the effective sky temperature can be much lower than the water's temperature, making the incoming radiative term relatively small. Net radiative loss may be strongest at first, while the water is warmer. As it cools, its own emission falls and the other heat flows matter more. With clouds and humid air, downward infrared emission increases, shrinking that difference. Convection and conduction can then offset much of the remaining loss, leaving the water cool rather than frozen. Radiation is therefore not cold poured onto the water. It is a power exchange, and cooling occurs only when outward flux exceeds inward flux. The exact performance of a Yakhchal cannot be assigned one universal value. Area, weather, materials, water depth, and construction all change the balance. The framework does show why a favorable night could provide a sustained route for removing energy. Radiation was not the only way the water could lose energy. At the surface, some of its most energetic molecules were constantly escaping into the air as vapor. Each molecule carried away latent heat, leaving the water behind slightly cooler. In very dry air, where that vapor could disperse rather than quickly returning as condensation, evaporation became an effective supporting heat loss path. Air movement could strengthen that effect by carrying moisture away from the surface, but wind was not automatically beneficial. A gentle flow of dry air could renew the air immediately above the water. A stronger or warmer flow could also bring insensible heat, disturb the carefully sheltered surface, or increase mixing with air that had not cooled beside the ground. The useful condition was not maximum wind. It was a favorable balance between moisture removal and unwanted heat transfer. There is an important limit here. Evaporative cooling tends toward the wet bulb temperature, the temperature reached when evaporation and the surrounding air conditions come into balance. In exceptionally dry conditions, that limit can be very low, and evaporation may contribute substantially to freezing. But evaporation is not interchangeable with radiative cooling. Radiation can continue removing energy from an exposed surface when the surface has already fallen below the surrounding air temperature, because the surface is exchanging infrared energy with the colder effective sky. That is the part evaporation alone does not explain. A thin water layer could therefore lose heat in two directions at once, infrared energy traveling upward and vapor carrying latent heat away through the dry air. Conduction from the ground, convection from the air, and later the energy required to freeze the water still had to be paid for. Evaporation was a vector in the heat budget, not a universal label for the whole freezer. At dusk, the most promising water was not necessarily in the deepest part of the Yakhchal. It could be spread in a shallow trench or pool on the cooler, north-facing side, where walls and orientation reduced direct exposure to the setting and rising sun. The thin surface looked modest compared with the eventual ice store, but that was precisely its advantage. It was a production surface, not a warehouse. Depth changes the problem immediately. A deep reservoir contains more water and therefore more thermal mass for every square meter of exposed surface. Heat must travel farther through that volume before enough of it reaches the surface and escapes. A shallow layer has less mass above the freezing interface and a shorter conductive path. Under the same nighttime conditions, it can respond more quickly to the loss of energy into the sky. The surrounding shade did not make the trench cold by itself. It protected the cooling budget. During the night, the open surface could see a large portion of the sky, while the walls blocked stray radiation from warmer ground and shielded the water from early sunlight. Timing mattered as well. Water placed or retained there before the clearest, coldest part of the night had more hours to shed sensible heat before the latent heat of freezing became the dominant obstacle. This arrangement also explains why the ice-making surface and the storage space should not be treated as the same feature. The trench favored exposure and rapid thermal response. A storage pit favored darkness, stability, and protection. Historical Yakhchals did not all share one layout or one operating routine, so the exact form of these freezing surfaces varied. The physical division, however, is clear. Shallow shaded water could be tuned to lose heat, while a large, deep volume would be better reserved for keeping the result. The dome's protective skin had to do more than look solid. A cross-section of sarooj would show a mineral-rich matrix pores and, in some descriptions, small reinforcing fibers. Saruj was a traditional waterproofing mortar, but its composition was not a single fixed recipe. Clay, sand, and lime are commonly associated with it, while organic additives such as egg whites and fibers such as goat hair appear in some accounts. Those ingredients and their proportions could change with region, materials, and the builder's practice. Their physical roles were not identical. Mineral particles and clay formed the bulk of the matrix. Lime could contribute to binding and durability after setting. Organic material may have altered workability or the size and connectivity of pores, while fibers could help limit cracking by bridging weak points in the hardened layer. These are material functions, not evidence that every sarooj wall contained every listed ingredient. The waterproofing mattered thermally because moisture changes the behavior of porous masonry. Dry pores interrupt heat flow and help a thick wall resist conduction. When water enters those pores, it can provide more continuous paths for heat transfer, and repeated wetting and drying can damage the surface through cracking or erosion. A water-resistant finish therefore helped preserve both the wall's physical integrity and the relatively dry, insulating structure beneath it. That did not turn sarooj into an airtight or magically heat-proof coating. Its value came from protecting a thick earthen envelope whose resistance accumulated across many layers. The mortar kept water from undoing that resistance, while the masonry delayed heat reaching the interior. In the Yakhchal, waterproofing was consequently part of thermal control, not because the plaster created cold, but because it helped the structure remain a dependable barrier against heat and moisture. Seen against the sun's path, the cone looks less like decoration and more like a way of distributing solar exposure. A flat roof presents a broad surface that can receive strong direct sunlight during part of the day. A sloped shell turns different faces toward the sun at different times, reducing the long, uninterrupted exposure of one broad horizontal plane. The exact advantage depends on latitude, season, orientation, and surface finish, so the slope was not a magic shield, it was a way of managing solar input. The shell also supplied substantial thermal mass. Thick earthen walls absorb heat slowly, and the heat that enters during the afternoon does not instantly reach the protected interior. It moves through the material with a delay, while underground spaces and shaded surfaces can begin from a cooler state. The cone's height and narrowing envelope also sheltered a large interior without requiring an equally broad exposed roof. In designs with protected openings or upper finishes, the structure could further limit direct environmental exposure. Those details varied, and the shape alone could not manufacture cold. Its value came from cooperation. The sloped shell moderated solar input, its mass delayed heat penetration, and its surface could be protected against moisture. The cone organized a durable barrier around the spaces where ice would later be preserved. Once ice had formed, the Yakhchal no longer needed the same environment that produced it. The freezing trench had exposed water to the night sky. The underground reservoir did almost the opposite. Its task was to hide the ice from the sun, from moving hot air, and from sudden changes in outdoor temperature. Burial supplied the first protection. Soil does not follow every outdoor temperature swing immediately. Heat moves through it slowly, so the deep chamber experienced a delayed and softened version of the surface climate. A hot afternoon could raise the outer masonry while the earth around the pit remained comparatively stable. That did not make the ground cold forever, but it reduced the size and speed of the heat pulse reaching the ice. The boundary around the chamber mattered as well. Thick masonry, dry earth, and a moisture-resistant surface such as a carefully made sarooj coating could slow both heat flow and water movement. Saruj recipes varied, so it is safer to think of it as a family of mineral-based protective mortars rather than one fixed formula. Its value here was practical. A dense, durable skin could reduce cracking and limit dampness entering the storage space. The pit and the freezing trench therefore had different jobs. The trench favored a large exposed area and a shallow water layer because those features allowed heat to escape quickly. The pit favored darkness, thickness, and as little exposed ice surface as possible. Ice could be accumulated in layers or blocks, depending on the local operating practice. Packing it closely reduced the area in contact with warmer air. Where the construction allowed meltwater to drain away, that also mattered because liquid water touching the remaining ice could carry heat into it and accelerate melting. No underground store was a perfect refrigerator. Some ice would melt, especially near walls, entrances, or imperfect joints. The engineering objective was not to eliminate that loss, but to make the loss slow enough that a winter supply could survive into the season when it was most valuable. The chamber acted as a thermal buffer. It converted a brief freezing opportunity into a controlled, gradual release of cold. That gradual protection could be assisted by the air above the chamber. In a vertical passage, air warmed by the sun or by contact with warmer surfaces becomes less dense and tends to rise. If the structure provides a route upward, that buoyant motion can create a pressure difference. Warmer air leaves higher up, while cooler, denser air occupies lower regions. A tall conical shaft, and in some designs a more complex or spiral passage, gave that movement room to develop. The point was not that the cone automatically pumped cold air downward. Rather, height increased the distance over which a temperature difference could act, while openings at different levels created a possible path for circulation. Warm air near the upper part of the structure could rise toward an outlet instead of remaining trapped over the storage zone. This could help with moisture as well. Air carrying water vapor that escaped from wet surfaces or entered through access points might be vented upward. Drier air is generally more capable of accepting further evaporation, so removing humid air could support cooling at exposed surfaces. But ventilation was only one contributor. It could also bring hot outside air inward if the opening's wind or temperature difference favored that direction. The strength of the draft depended on ordinary physical details: the height of the passage, the size and placement of openings, the temperature difference between lower and upper air, wind pressure, and friction along the walls. A narrow channel offers resistance. A wide opening may admit unwanted heat. A still day and a breezy day would not operate the same way, so the vertical shaft was best understood as a controllable pressure path, not an autonomous air conditioner. It helped the dome shed warm and humid air when conditions supported upward flow, while the buried mass and insulated boundary limited the heat that could replace it. The airflow made the storage environment easier to manage, but it could not compensate for a poorly sealed chamber or an unfavorable climate. The whole process becomes clearest over a single night. Before or during the evening cooling period, water was distributed in shallow freezing trenches, often positioned to avoid direct sun, and in some arrangements favor exposure toward the open sky. A thin layer was not a smaller version of a deep pool. It had a much shorter distance for heat to travel, so its temperature could respond rapidly when the surface began losing energy. At dusk, the direct solar input disappeared. The water still exchanged heat with the surrounding air and the trench walls, but it could now emit infrared radiation toward the relatively cold, clear sky. At the same time, evaporation carried away latent heat. If the air was dry and the surface remained exposed, that evaporative loss could continue to assist the radiative loss. The water did not need to become colder than the air by magic. It was losing energy through several paths at once. The heat balance changed as the night progressed. First, the water lost sensible heat, meaning its temperature fell. Then, if the surface reached the freezing point, further energy removal could begin converting liquid water into ice. That phase change is the demanding part. The water must surrender a large amount of latent energy, even though its temperature remains close to the freezing point. A shallow layer gives that threshold event a chance to arrive before dawn. But the outcome was conditional. Cloud cover can return more infrared energy from the sky. Humid air can reduce the effectiveness of evaporation. Wind can either improve exchange or bring warmer air across the surface, and deeper water requires more energy removal. A cold, clear, dry night was an opportunity, not a guarantee. By morning, any formed ice had to be treated as a material to preserve rather than a surface to keep exposing. Workers could move or gather it into the protected underground store, where the large exposed area of the freezing trench was no longer useful. The operation changed objectives in one night. First, remove heat quickly from a thin layer, then restrict every practical route by which heat could return. To test whether that ice could last through summer, the question has to be written as a heat budget ledger. On one side are the gains: conduction through the roof and walls, convection through entrances and vents, radiation from warmer surfaces, moisture moving through the construction, and heat carried in whenever the chamber is opened. On the other side are whatever cooling opportunities remain, especially at night or through limited evaporation near exposed areas. The design tries to make the gain side small. Thick walls lengthen the route heat must travel. Dry construction reduces the extra heat transport associated with moisture. A compact store limits the surface area available for exchange compared with the amount of ice inside. Shade reduces direct solar loading, while restricted access prevents every opening from becoming a daily channel for hot air. The surrounding Earth adds a time delay. Imagine a summer heat wave reaching the outside surface first. It does not instantly appear at the ice. Part of that energy is absorbed by the masonry and soil, and the rest moves inward gradually. By the time the warmth reaches deeper layers, the outdoor temperature may have fallen again. The enclosure is therefore not holding one perfectly constant temperature. It is stretching and weakening the daily temperature wave. A simple physical test would compare the stored ice with an exposed block of the same mass. The exposed block receives sunlight, exchanges air across its whole surface, and responds quickly to each warm hour. The buried block receives heat more slowly and from fewer directions. The difference would not be zero melt versus total melt. It would be a difference in rate, and over weeks or months that rate determines whether a useful reserve remains. That is the proper meaning of summer preservation. The Yakhchal did not suspend thermodynamics inside a permanently frozen room. It arranged enough resistance, delay, shade, and limited access that the seasonal heat entering the store could be kept below the amount required to melt the entire supply. That rate depended on whether that could change the result overnight. On a clear, dry night, an exposed water surface could lose energy toward the cold, effective sky faster than it received energy from the atmosphere. If the water layer was shallow and protected from daytime sun, its temperature could fall far enough for freezing to begin. Now replace that sky with a sheet of cloud. Cloud is not simply a visual obstruction. It emits infrared radiation downward, often at a temperature closer to the surface than the clear night sky does. The water still radiates upward, but the difference between energy leaving and energy returning becomes smaller. Add humid air, and evaporation also becomes less effective because the air has less capacity to accept more water vapor. The same trench may cool substantially, yet stall above freezing. Other failures are more local. A warm night reduces the time available for heat loss. Excessive wind can increase evaporation, but it can also bring warmer air into contact with the water and raise convective heat transfer. Poor shade lets sunlight erase the previous night's gains. Cracked or damp mortar creates unwanted paths for heat and moisture. Insufficient depth leaves stored ice too close to the daily temperature swing, while frequent opening of the chamber admits warm air and disturbs the protected thermal environment. These are separate weaknesses, not one universal failure switch. A well-built structure might tolerate one unfavorable factor and fail when several arrive together. That is why one successful freezing event demonstrates physical plausibility, not a guarantee that every desert climate, every season, or every Yakhchal followed the same operating schedule. The broad mechanism can be reconstructed from heat transfer. The exact routines of a particular site require direct evidence and should not be supplied by assumption. That distinction makes the structure useful to modern designers. Instead of copying a cone as a decorative object, a design translation board would match each old component to the heat path it controlled. The exposed freezing area corresponds to a surface designed for radiative coupling with the night sky. Its shade corresponds to selective exposure, open when the environment removes heat, covered when sunlight or warm air would add it. Evaporation remains an assist, while earth, masonry, and stored water provide thermal mass that slows temperature change. The underground chamber has clear modern relatives in earth-sheltered rooms and insulated thermal stores. A tall shaft resembles a passive downdraft or buoyancy ventilation route, provided there are suitable openings and a real temperature difference to drive the flow. Modern night sky cooling panels use the same basic opportunity more precisely. A surface is given a strong view of the sky while insulation limits heat arriving from below. Sensors can decide when to expose, cover, ventilate, or isolate that surface, replacing guesswork about changing clouds and humidity. Modern materials can improve the details without changing the logic. A waterproof outer layer can reduce moisture damage. Better insulation can limit conductive heat gain. Cleanable liners can address hygiene where water or ice is stored. A temperature and humidity sensor can prevent a hatch from being opened during the warmest part of the day, or reveal that a cloudy night is not worth exposing the cooling surface. But none of those upgrades creates a universal refrigerator. Local cloud cover, humidity, groundwater, maintenance capacity, water availability, and sanitation still decide whether the design is appropriate. In a humid city, a radiative surface may need a different balance of insulation and moisture protection. Where nights stay warm, the system may cool water without freezing it. The transferable idea is more exact than simply building underground. Use timing, sky exposure, thermal buffering, and controlled airflow so each part works during the environmental condition that favors it. Taken together, the Yakhchals solved two different thermal problems in sequence. Favorable nights created an opportunity to remove energy from exposed water. Then the structure's buried mass, thick earthen envelope, shade, and moisture protection slowed heat returning to the ice. It did not make the entire building cold. It matched each task to the condition that favored it, turning a brief nighttime advantage into a summer reserve. Which part of the Yakhchal seems most ingenious to you? The night sky radiator, the freezing trenches, the Saruj shell, or the subterranean ice store? Subscribe for carefully researched explanations that follow historical technologies from materials to mechanisms and real-world limits. The Yakhchal was not a single magical cooling trick but a coordinated heat management system. The sky served as a nighttime heat sink. Evaporation and airflow assisted the approach to freezing. Saruj and mass slowed heat gain, and the underground store turned a brief cold opportunity into a summer resource.